morning. Derrick Robert Irumba is my name, and I'm presenting a study with, in conjunction with Professor Anthony Gidudu and Dr. Lydia Mazikayondo. And it's about analyzing spatial susceptibility, spatial-temporal susceptibility of wildfire susceptibility in Queen Elizabeth National Park, that is in western Uganda. That is the presentation outline, and I will start with the research background. Wildfires are defined as unwanted fires that happen in grasslands, vast lands, abandoned agriculture fields, and these usually happen in these areas and are uncontrolled in nature. Now, it is been documented that in the sub-Saharan region of Africa, that wildfires are at an increase, and this is because of existence of vast grasslands, but also due to conducive climatic conditions, whereby there is a cyclic occurrence of dry and wet seasons, whereby the dry seasons encourage the drying out of vegetation, making it very flammable. And in the previous wet season, you'll find that the wet season has encouraged the growth of these vegetations. So the recurrence of these cycles bring about conditions that are very good, or that enable thriving of wildfires. And given that wildfires have negative impacts on wildlands, in that they distort habitats or destroy habitats, but also lead to loss of biodiversity, these negative impacts can be very disastrous and thus should be mitigated against. In an effort to curb these wildfires, management of protected areas, such as that of Queen Elizabeth National Park, carry out preventative and also suppression mechanisms, whereby preventative mechanisms are applied before wildfires occur, and these include practices such as controlled early burning, and suppression mechanisms are these that are applied on the onset or during occurrence of wildfires, and these can include fire extinguishing. It should be noted that these practices, the preventative practices such as controlled early burning, have been continuously been applied in the Queen Elizabeth National Park, but however, wildfires have continued to thrive. This is because of their poor application due to lack of information about wildfire-prone areas within the park. Also, the capacity of the park to sustain suppression mechanism is limited due to inadequacy of funds. This is because equipment such as pumper trucks that are used in these approaches are very expensive. So for effective application of both preventative and fire suppression mechanisms in an effective way, you need to have a knowledge base as prescribed by the Food and Agriculture Organization. So this research comes in to provide information of fire-prone areas to enable effective application of these mechanisms within the Queen Elizabeth National Park. It should be noted that information of fire-prone areas and also behavior and patterns of wildfires should be updated periodically. But you find that in Queen Elizabeth National Park, studies that have been related to such have been date back as far as 1976 and also the late 2000s, which makes this data very obsolete. Therefore, there is need to update this information, whereby this research comes in. So, for better management of fire-prone areas, as previously discussed, there is need to integrate fire risk assessment into fire management, and this includes modeling of fire susceptibility to determine areas that are prone to wildfires. As discussed, as stated before, the study area is Queen Elizabeth National Park, which is a protected area in the western part of Uganda, and it covers an area of about 1978 square kilometers, and it is uniquely divided into the northern and southern sectors by a waterway that is called the Kazinga Channel, which connects Lake Edward and Lake George, whereby Lake Edward is on the western side and Lake George is on the eastern side of the study area. The objectives of the study, the first is to study the spatial-temporal variability of wildfire susceptibility in Queen Elizabeth, which is the general objective, with the specific objectives being to characterize the relationship between wildfire conditioning factors and the locations of wildfires within the study area, and the second one to model wildfire susceptibility. Now, you will realize that I use fires and wildfires interchangeably. This is because most fires within the study area are uncontrolled and malicious, and therefore most of them are wildfires. So that is the assumption we are taking. The data sets that were used in this study include satellite data, whereby MODIS and VIRS, that is moderate resolution imaging spectrometer, and the visible infrared radiometer suite that were used to determine wildfire locations or create an inventory for wildfires. Then ASTER DEM that was used to obtain topographic factors. Then CHAPS rainfall data that was used for rainfall or precipitation data. Then Landsat that was used to characterize vegetation using the normalized difference vegetation index. I will discuss this later. And then vector data such as roads, villages, lakes, and rivers for proximity factors. The methodology that was developed for the study is shown in the flowchart. First and foremost, in order to determine wildfire susceptibility, the weights of evidence method, which is a statistical Bayesian form of log linear modeling, was used in this study. And this is used to give a statistical relationship between a factor and an event. The event in this case, which is wildfires. In order to do so, first an inventory of wildfire locations was created. And as previously stated, this was done using MODIS and VIRS satellite data. And this was acquired in point format. Preprocessing was done on this data including clipping, but also error analysis. Error analysis was done to eliminate locations with errors of commission, that is false detection. And after this, exploratory spatial data analysis was carried out on the data in order to obtain patterns and trends, and after which random subset was carried out. This was done in order to obtain training data and validation data, whereby the training data was 70% and the validation data was 30%. So after which, we go to the wildfire conditioning factors. Now, the wildfire conditioning factors, there is no clear agreement on which factors really determine wildfires from place to place. However, depending on the conditions of the study area and also literature about the study area, you get to determine which factors to consider while carrying out wildfire modeling in a given area. Now, for this case, topographic, climatic, vegetation, and proximity factors were considered. And for topographic, slope, aspect, and altitude were considered. Then for vegetation, the normalized difference vegetation index was used to characterize vegetation. And in regards to climate, precipitation data was used. Some of these data sets were applied because of availability. Data sets such as temperature were not considered because of lack of this data within the study area. Then for proximity factors, distance to roads, distance to villages, distance to lakes, and distance to rivers were considered. All this data was pre-processed, various pre-processing was done, and after which multicollinearity diagnostics were carried out. This is because the weights of evidence method that was applied in this study requires for all conditioning factors, which are also the explanatory variables, to not to be correlated. So the multicollinearity diagnostic that was applied was the various inflation factor, whereby the critical values should be below 5. So after which, using the 70% training data and the wildfire conditioning factors, now the modeling happened. The spatial relationships were obtained. I will discuss this more. The spatial relationships are obtained using what they call the weights of contrast, and the significance of the relationship is obtained using the value which is called the final weight. This will be discussed further, from which the first specific objective was obtained. Now, from these, multi-class weighted variables were obtained, which were spatially overlaid numerically to obtain the first model. In the first model, all the wildfire conditioning factors were considered, that is both for MODIS and VIRS. In order to validate the performance of the model, the receiver operating characteristic area under the curve method was used using the 30% validation data. Now, this would give the performance of the model. Now, remember, at first, the first model or the first two models included all the variables. However, in order to determine the performance of each wildfire conditioning factor or its influence on the model, a variation was made using by omitting one variable at a time, and upon which the receiver operating characteristic was also computed to determine the performance of the model at that point. Now, the best performing model for each set of data set, that is for VIRS and the MODIS derived, was used to obtain the wildfire susceptibility index map, with the best performing used to derive the wildfire susceptibility for the study. Now, from the results, you realize that on the left, the map shows the distribution of wildfires, and MODIS had 534 wildfire locations within a period. The period was running from 2015 to June of 2021, while VIRS had 1585 wildfire locations. This shows that VIRS has more or detected more, and this is expected because VIRS has a higher spatial resolution as compared to MODIS. Now, from both data sets, 60% of the total, approximately, was located in the northern sector, and then 40% within the southern sector. This is also in accordance with previous studies that have observed this, and it is because the northern sector is attributed with very large expanses of grasslands that provide very flammable fuel. On the right-hand side is the graph that shows the monthly distribution of fires, whereby the fires peak twice within a year, that is in two seasons, January to March, and then June to August, with the January to March being the first dry season of the year, and then the June to August being the second dry season of the year. The first dry season of the year was observed to contain or more fires as compared to the second dry season of the year. This is because the first dry season is characterized by really higher temperatures as compared to the second season of the year. The higher temperatures lead to drying out of vegetation that makes it more flammable. Also, these seasons correspond to seasons whereby farmers prepare fields for agriculture. In preparation of fields for agriculture, there are practices such as burning of dried out biomass in these fields that can easily result into wildfire occurrences. These are the wildfire conditioning factors. Now, a notable absence in these factors is slope, and from the results, it was discovered that the variability of slope was really poor, and it was giving bad results. So it was eliminated from the analysis. Now, the table shows the spatial relationships as previously discussed. From the weights of evidence method, the value of C, which is also the weights contrast, determines the spatial relationship, and the W final, which is the final weight, determines the significance of relationships. From those results, what can be seen is that if you have a value of C that is equal to 0, then there is no relationship between a wildfire conditioning factor, category, and occurrence of wildfires. And a positive value of C indicates a positive relationship, while a negative value of C indicates a negative relationship between a wildfire conditioning fire category and the wildfire occurrence. Then the higher values of W final indicate a higher significance of relationship as compared to the lower values. Now, this table shows the values for MODIS, and then the next one shows the values for MODIS. You may not necessarily follow the values, but I will give out extracts from the figures. Now, these values show that the MODIS and VIAS relationships that are derived are similar, and this is because both data sets were obtained during this same time frame. So the relationship is the same. VIAS weights final are a bit higher, indicating higher relationships, significance of relationship as compared to MODIS. This is because since VIAS has a higher spatial resolution, it has a higher detection range and a higher variability, implying stronger relationships. Then aspect relationships with fire occurrence indicated very low significance. This is because the study area is located at the equator, and the effect of the sun on different aspects is very low. Then an increase in altitude was inversely associated with the occurrence of wildfires. Generally, low NDVI values were observed. This is because the satellite images or the Landsat images were obtained during the dry season. So this is expected. But also, lower NDVI values were highly related with the occurrence of fires as opposed to the values that you see that are higher than 0.5. Also, increase in mean annual precipitation was observed to be negatively associated with the occurrence of wildfires. Proximity factors provided rather surprising results, with distance to roads showing very low significances of association with wildfires. The reason behind this is that national roads were used instead of feeder and trail roads, and it is known that these feeder and trail roads are more associated with malicious activity that could lead to wildfires. Also, locations very close to water bodies such as lakes were negatively associated with wildfire occurrence. This is because these are associated with activities such as fishing and trade that are not associated with the occurrence of wildfires. However, locations that were a bit further were associated with wildfires because these are locations in which farming, beehive, honey keeping is carried out, and these were highly associated with wildfire occurrence. The result from wildfire susceptible modeling indicated that the models were indicated good performance for both MODIS and VIAs, with VIAs showing higher performance than MODIS. Of course, this was previously explained. All models with all variables considered showed the highest performance, indicating that the various factors are responsible for the occurrence of wildfires. Exclusion of variables from models were slightly sensitive to model performance. However, distance to lakes, NDVI, and altitude showed they showed a decline in performance of models, implying that these factors had a higher contribution or influence towards model performance. From the wildfire susceptibility maps that were developed, most fires were located within areas that were highly susceptible, and this is in accordance to the assumption of the weights of evidence model that says that the application of weights evidence model assumes that future wildfire occurrences occur in places with similar conditions that contributed to past events. This is because these occurrences were attributed to existence of vast grasslands that provided for fuel for those fires and also socioeconomic activities, as earlier discussed. Wildfire susceptibility maps were categorized into 5 levels, with levels ranging from low up to very high. Now, it can be seen from the graph that 19% of the study area was categorized to be at a very high risk of wildfires, while 20% at high risk, leaving 61% with moderate, low, and very low risk. In conclusion, we can see that the occurrence of fires within the study area is largely seasonally dependent, and this narrows down the time within which wildfires occur within the study area. Also, the conditioning factors, altitude, NDVI, and proximity to lakes, were found to be most influential in determining the occurrence of wildfires. Now, the weights of evidence method provides a good success rate with 70% and 68% for MODIS and VIAs respectively. However, this can be built upon for future studies to enable studying of wildfire occurrences. The results enabled narrowing down of the study area to show the areas that are more prone to wildfire occurrences. Now, from the recommendations, that this study can be upscaled and used to develop early warning systems on the onset of wildfire seasons. Also, highly susceptible areas should be a concern to management, and since they have been narrowed down to about the 20%, the 18% and the 20% that are very highly susceptible, this provides a focus point for management to apply fire prevention and fire suppression. Also, future research should consider inclusion of other factors that are documented to cause wildfires within the study area. And the study should be extended to areas or protected areas with similar fire hazard issues. The main limitation of the weights of evidence method is it provides a similar weight for all wildfire conditioning factors. Therefore, as a recommendation, future studies should consider including or applying it in conjunction with other modeling weighting techniques in an in an approach that is known as ensemble modeling. Thank you very much.
Thank you very much, Derrick, for that good presentation. I will invite questions from the audience. Do we have any questions? Okay, I also don't see questions online, but I have a few of my own. Just about 2-3 questions. What would you recommend as the frequency of modeling fire susceptibility? And then what could it be possible to consider sensitivity analysis, because we are seeing a lot of interaction of variables. Maybe some is being lost to non-linearity. So maybe we would love to look at sensitivity analysis. And then you talked about the difference between fire and wildfire. How were you able to establish malicious fires?
Okay, I will start with the last question. In the preamble to the study area, I hinted that within the study area, majority of wildfires are malicious, and the study took on the assumption that since majority of the fires within the study area are malicious, then all fires that are obtained are considered as wildfires. However, refinement can be made with future studies to provide criteria to differentiate between malicious and wildfires. Then for the part of sensitivity analysis, in this study, specifically, we look at elimination of a wildfire conditioning factor and the performance of the model when that wildfire conditioning factor is applied. However, other sensitivity analysis methods can be applied on the same to get even better results. I would just like a recap on the first question.
The first question was, what would you recommend as the frequency for modeling fire susceptibility, since you indicated that there was a problem with it?
Yes. Various literatures indicate that wildfire susceptibility should be carried out at least every 5 years. This is because human-led factors or influences change from time to time, and therefore within a 5-year frame, there should at least be a study carried out to update or to build upon the previous studies that have occurred.
Okay, if we indeed have no further questions, thank you so much, Mr. Derrick.